not like he was giving them anything. It's not like he stopped work.
Yeah, good point.
Make their marking.
Yeah.
That's so dumb.
Yeah, it's so annoying. Oh, it's really annoying. And now I have to prepare again. I mean, like, at least I know what I've sent over. But it's annoying because I had spent like a week prioritising. I screwed up the first week. And now I was probably ahead of where most people would be, but I haven't spent all the time. And now everyone's telling me, oh, it's really annoying.
Oh, well.
At least it's kind of funny to like observe the context.
Yeah.
Like the group chat's going off as well.
Is that lecturer just
Oh, he's so lazy. And he writes like a child as well. The handwriting, honestly, like of someone in grade 2.
Yeah, that's pretty good. Alright, let's go get started. How many rounds are this?
I've got the one other maths subject. And then biology. Yeah.
Maybe my favorite option.
Okay.
He's such a good workshop. Yeah, he's so good.
You kind of just, it's like a public event.
Yeah. Just listen to him like every time. And he's got the notes and just.
Actually, I went there.
Did you?
Okay. Let's make a start, shall we? So we're studying semiconductors, and it'll be pretty straightforward today. Again, if any of you have any questions, please feel free to email me, and I'm happy to answer any questions you have. So semiconductors, historically, at the very start, were not very well understood. And the famous physicist actually said one shouldn't work on semiconductors. That is a filthy mess. Who knows whether any semiconductors exist? So they were quite confusing at the time. Okay, so they're a really important material. They're in many of our electronic devices, computers, laptops, CD players, very, very many things. So let's have a look at the kind of materials that they are made of. We can see here the silicon. Here, that was, this is a very popular one, used in many devices at the moment. Earlier on, there was germanium that was used, and you can get quite high quality germanium crystals. Compound semiconductors, gallium arsenide, indium gallium phosphide. So we have binary compounds, ternary compounds with 3 components, and even quaternary compounds with 4 different components. And why do we like to have different components? Because you can engineer their characteristics by mixing the concentrations in the way that you want. You can engineer how the band gap is, which is one of the key properties for these materials. 20 years ago, there was a big development. You know how we have many different kind of LEDs now. We have green and blue, as well as red and amber. These were the first ones to be developed, and you know it's only the last 20 years that gallium nitride and its other members, aluminium nitride and indium nitride, have been developed that allow now the full spectrum of colour for the solid state lighting. Okay, remember we had a slide showing the difference in conductivity. The insulators were here, about 10 to the minus 18 per ohm per meter. Semiconductors, we are here in the middle, and they have quite a range of conductivity. And we had here, the metals that were highly conductive, and even the superconductors, which had extremely high conductivity, but which we're not dealing with right now. So, just to classify some different names here, we like to break them up into elemental semiconductors, which means just the pure material. For example, silicon and germanium from column 4 of the periodic table. So they just have one species. And then we have compound semiconductors, which means we are mixing different materials together. In particular, from the column 3 and column 5 of the periodic table, as well as column 2 and column 6 of the periodic table. And as I mentioned before, you can even mix 4 elements together if you are building some kind of special semiconductor device. So here we are. This is column 4, where the elemental semiconductors are, and we can make various combinations. For example, aluminium with phosphorus, gallium arsenide, indium and antimonide from the 3-5 semiconductors is a very well-known family, and also the 2-6 combinations, zinc selenide, zinc sulfide, and so on, listed here. So these are the main semiconductors that are in use, but we should also now add to that the nitride family, which are really important family of semiconductors. So there, if you look at the periodic table, that's where they are located. All right, that's column 4. You see the carbon, silicon, and germanium ones there. And then right next door you have column 3, your elements that have 3 valence electrons over here, and they are combined with the column 5 ones, which have 5 electrons in the valence shell. Okay? And then the 2-6 ones are here. You have here the zinc selenide, zinc telluride, cadmium selenide, and so on. Okay, this sort of gives a bit of background. Why are they so important? Because, as I said, you can engineer their properties by mixing the different components. So at the early days we had germanium, and silicon is now really, really in heavy use. But we're going to have to develop new semiconductors than silicon, because silicon is almost at its level. You can't really make nanostructures small enough in silicon, and we're looking for ways to perhaps integrate with the silicon or actually change the technology completely. What else here? Yeah, a lot of this engineering is done by doping. It's called doping the semiconductor. So what that means is you deliberately add impurities. Say, for example, you've got a chunk of silicon and you might add a phosphorus atom, and by doing that at a very small concentration, okay, you only need 1 part per million, and you will change silicon from being a poor conductor to being a good conductor. So when you dope, you just need very small concentrations of the dopants. Okay, so when we have a pure semiconductor without dopants, we call it intrinsic. Okay, and when we say it's intrinsic, it still does have some impurities, because it's really hard to make a very pure semiconductor. So typically your material might have 1 part per million to 1 part per billion impurities in your material. Okay? But that's kind of the best you can do. With the exception of germanium, that can actually be grown quite purely. Okay, so if we have, say, a semiconductor, an intrinsic semiconductor at 0 temperature, here's a schematic of your, say, silicon atoms in their tetrahedrally coordinated environment. And as you know, each of the silicon atoms has 4 electrons in their valence shell. So the silicon atoms bond to 4 more silicons, and then they can share those electrons with each other and make this nice covalent bonding, which is sketched here. And at 0 temperature, it won't be conductive because the valence band will be completely full and the valence band will be completely empty. Okay? Now, if you introduce some temperature, what you'll create is some electron-hole pairs, which means some of the electrons from the valence band will be excited up into the conduction band. And so in these materials, these are the only kind of carriers that you get if we're just neglecting the impurities that will probably be there, but we're not considering those. We're assuming that this is an undoped material. So the only carriers in intrinsic material will be these electrons and holes, and they occur in pairs. Okay? So if you have your atom here, due to the thermal energy, some of those electrons can get excited into the conduction band, and behind them they will leave a hole, which is indicated by H+ here. Okay? And because we have charge neutrality, the number of electrons that are excited will equal to the number of holes left behind. Okay? And so what we do is we use the notation Ni means the concentration of electrons. The I just means intrinsic, that you've got these are the intrinsic ones, not the ones that are actually deliberately doped. Okay, and P means the holes, the concentration of holes. And in these intrinsic materials, the number of electrons carriers are equal to the number of holes. We'll get to holes a bit later on. Those are just the electron states that are left unoccupied in the valence band. Okay, is anybody familiar with holes already? Okay, good, yeah. Okay, so what I want to emphasize here, when you're doping your semiconductor, this is a way you can control its characteristics in addition to mixing with different atomic species, different compounds. Okay? And these very small amounts can have a big influence on the conductivity of the semiconductor. And there's a lot of research, in the semiconductor industry, for example, trying to grow very pure materials so that you can know exactly what you've got in your material, and so that you can control the properties. Often they will be doing studies and they will see from their experiments that they have some kind of contaminants, and there's a lot of effort trying to identify what those contaminants are. I don't think I talk about it in this talk, but there's also native defects that play a role. For example, you might have a vacancy, a silicon vacancy. You might have some kind of anti-site, which is, if you've got, say, gallium nitride, you might have a nitrogen on a gallium site and a gallium on a nitrogen site. That's called an anti-site. And these defects, they're called native defects, they can also contribute to changing the properties of your material. Okay? So that's another reason it's very important to try and grow these materials without any defects or impurities. Okay, so the main point is if you are doping your system, you just need to do very small concentrations. We'll have a little look at it down here. And the two types of doping is N-type doping and P-type doping, electron doping and hole doping. Now, so what is the kind of levels that we have? So normal doping levels, that is the kind of concentration of dopants that you might introduce into your system, are of the order 10 to the 19 to 10 to the 23 impurities per meter cubed. So if you just remember those kind of numbers, it gives you a good order of magnitude. And remember that silicon has a concentration of about 5 times 10 to the 28 atoms per meter cubed. So that kind of gives you an order of magnitude comparison of how many impurities you'll have per how many atoms of your native species. Typical values for intrinsic carrier concentrations are about 10 to the 16 electrons and holes per meter cubed. So the intrinsic carrier are, remember, the ones that exist there already and contribute to a kind of background conductivity. So these numbers are sort of normal kind of numbers. Okay, so let's look at, we're going to do an example mainly of silicon, and we're just going to look at what happens when you dope your silicon. So if we look at the electronic structure of silicon, you can see that this is the electronic configuration. You have 1s2 for the first shell here, 2 electrons in that shell, 2s2, 2p6. So in the second shell here, you've got filled with 8 electrons, all your states are filled. And then for the most outer shell, the 3 shell, if you like, you've got 2 s electrons and 2 p electrons. So this is indicated with the 4 electrons in your outermost shell. So that's just basically what we have said there. And as you know, silicon forms strong covalent-like bonds. And, you know, it would prefer to have a filled shell, which means it really wants to have 8 electrons in its outermost shell. So that's why it bonds in a tetrahedral environment. So it has got 4 other silicon atoms that it bonds with, and they can share their 4 outer electrons. So each bond will have 2 electrons in it, which is what it wants. Okay, so schematically, you can think of the silicon sort of as shown here. At t equals 0, it's got its 4 valence electrons, the outermost ones, and it bonds to 4 others. And each one contributes 1 electron to the bond that it makes with the other silicon atom. And at t equals 0, the valence band is completely filled and the conduction band is completely empty. So it carries no current. Okay? But for t greater than 0, you have thermal fluctuations, and the electrons have enough energy to break free of their orbit, if you like, and leaving a hole behind, which is indicated here by the open circle. And then these two, depending on the energy, can propagate throughout the crystal. Okay? So that's why it becomes conductive at higher temperatures, or at least mobile. Yeah. So schematically, you can think of it like this. Now, when we draw a band structure, this is just showing a little bit of the silicon band structure, just around or just a general valence band, where blue indicates it's completely filled with electrons. Empty conduction band. This is a direct band gap semiconductor because the valence band maximum is at the same value of K as the conduction band minimum. And when you have excitation, be it either by thermal energy or by light, for example, you will excite an electron, for example, from here up into the conduction band. So now you have an electron in the conduction band where it can move around the crystal, and you have a hole, an empty electronic state in the valence band that can also move around the crystal. And the electron, as you know, is negative, and the hole is regarded as being positive. So this kind of plot will be familiar to you by now, I think. Remember from earlier on, this is the density of states drawn here for a semiconductor, if you like, or we don't have values of the gap, so it could also be an insulator, but it can't, well, it could be metal depending on how we filled it up. In any case, this is the density of states. Remember, this is a Fermi-Dirac function for some temperature, where the normal step function has got smeared out. And so when you actually plot the density of occupied states, you'll get something like this. What you'll see is there will be some states that have been depleted from the valence band, and they will become occupied up here in the conduction band. So it's kind of interesting to think, I mean, you can only get quite considerable conduction if your band gap is pretty small, okay? If you have a band gap, for example, diamond 5.5 or magnesium difluoride has a very large band gap of 11, it will always remain an insulator, okay? So it's too big. But it's interesting to note that a material that wouldn't be a metal according to our definition, remember the definition was there has to be a finite density of states at the Fermi level to be a metal, but we can have a material that exhibits conduction but is not a metal, okay? So that's what a semiconductor is, okay? But it needs some thermal energy and a very small band gap, or we can also do doping, okay? And we'll see how what doping will do. It introduces additional electronic states in your band gap, okay? So if you have some dopant here, you'll get an extra density of states here that may be occupied by an electron or it may not be occupied. So yeah, that's the mechanisms by which doping can control your material properties. Why I've got the line there is just to differentiate between roughly what might be regarded as a semiconductor with the band gaps, very small band gap here for indium antimonide, 0.18, silicon 1.11, and anything, this line here kind of goes from being what's regarded as a semiconductor. You may also go up to 3 or something like that for the band gap, and then an insulator has a larger band gap. Okay, this coming back to the effective mass.
Yes. Does the gap size change with the temperature, or is
Let me think. That's a very good question. Does the gap size change with temperature? Yeah, no, it's a very good question. I don't know offhand. I think it may change slightly, yes, because we're having some, different occupancies of the bands, but I'm not sure offhand what the function of that is. That would be interesting to look at, yeah. Now I want to come to the effective mass. Remember we looked at the effective mass in some earlier slides, okay? Let's just recap what it is. It's basically the mass which the particle appears to have due to its behavior in the crystal, for example, when it responds to forces. So it's not a real mass, but it's a mass like the way it responds to things in the crystal. So, for example, we had from band theory that the movement of particles in the periodic potential is quite different to that in a vacuum, right? In a vacuum, the electron mass is just 9.9 0.11 times 10 to the minus 31. But in a periodic potential, the effective mass is not that value. Okay? The way we define effective mass, remember we had this equation here. We represent the effective mass as m star, it was h bar squared, over the second derivative of the energy dispersion curve. Okay? So this can be thought of as the curvature. Okay? So if, for example, we look at the conduction band, the curvature is positive. Okay? And so the curvature is positive, our effective mass is positive. Now in the valence band, it's curving downwards, so the curvature is negative, and so the effective mass in this case is negative. The effective mass is normally expressed in terms of the real electron mass, so you don't normally give it a value in kilograms, you normally say, okay, it might be 0.01 ME. Okay, so the effective mass is normally given just as a number, for example, 0.01 up to 10, but in some materials it can even be really quite large. So we give the effective mass, m star, in terms of the normal mass of the electron. So, okay, we'll move on a bit, but the important thing here is that we have a negative effective mass for the valence band maximum area. So this is basically what we did before. We just express, we say this is like a parabola, so we can just expand the expression for energy in terms of a quadratic here, just like a h bar squared k squared on 2m, okay, but now it's the effective mass. And we'll do the same thing for the valence band here. So for the conduction band, it's kind of straightforward. We have electrons up there, here being the conductive particles, they'll jump up here. Electrons up here, they have charge Q as minus E, as usual, and their effective mass is greater than 0 due to this curvature up here. For the opposite case, for the valence band maximum, we do just the same kind of thing here, except we're approximating it. The parabola obviously goes downwards, but we still assume it's a quadratic form going downwards. But when you think about it here, the charged particle, if it's an electron, it has this negative effective mass, okay? And that's, what does that mean? It means that the electron will respond to, for example, an applied electric force in the opposite way that it usually does. So instead of, if you apply electric force in this direction, the electron will normally go in the opposite direction. But at this, if it's in this band here, these kind of particles will go in the same direction. Now that's kind of queer, so this is how the concept of hole comes about. Okay? So for a hole, it has a positive charge, and we just say it has a positive mass. So the electrons will jump up here. You have states here which can be thought and described of as holes, empty electron states. Let's have a look at some typical kind of values here. So what do we have? We have, if you can think about this, this is the electron effective mass, so it's up there in the conduction band. And this is the hole effective mass, so that's down there in the valence band maximum region. So I wanted to plot out these two. These two would be better to plot out, but I didn't have time, but I plotted these to out the actual band structure. So you can see that, okay, for germanium, the electron has a greater effective mass than the hole. So the conduction band should have a different curvature to the valence band, where the hole effective mass is derived from, and the silicon has slightly the opposite case. Yeah, these numbers are sort of kind of similar. I wanted to plot out one that's got a much different, like here you can see the electron effective mass is really small compared to the whole one. Maybe I'll show that next time. But let's just have a look at the silicon and germanium comparison. Try again. Let's see. It's not coming up. Never mind. Never mind. I can show that next time. All right. So, yeah. Actually, next time I'll bring a comparison of these two. So what it's just interesting to see how the curvature of the bands differ from the conduction band to the valence band, and the correspondence of these two values that you get. Okay, so you can imagine it again in a different way if you like. Sometimes you might draw your valence band like this, just like a continuum, and the black dots represent filled states. And at some temperature T, here, this is your conduction band, you have excitation of the electrons up into the valence band, conduction band maximum. And as I said before, when you get this empty hole and the electron up there, these are called electron hole pairs. Okay? And these are the only particles for conduction for intrinsic materials. Okay, remember we talked about the conductivity of a metal as a function of temperature? Well, this is a plot for the conductivity of a semiconductor with increasing temperature. And so you can see here, as the temperature increases, we get an increase here in the concentration of carriers, and also we'll get an increase in the conductivity. Okay, so that's different to metals. And that just makes sense because you know that you've got more electrons being excited from the valence band up into the conduction band due to that thermal energy. So I think we can consider now here, we are doping silicon with a donor and an acceptor. Okay. First of all, let's look at a donor. So here we've got the silicon lattice. In this case, we've replaced one silicon atom with a phosphorus atom. Okay, now the phosphorus has one extra electron compared to silicon, and so the phosphorus will form nicely the electronic bonds with the other silicon atom, but there will be an extra electron left over. Okay, so it's drawn over here. So this phosphor can be represented as like just being a normal silicon atom. It's being called Si, silicon now. But you've introduced an extra electron into your system, but also you've obviously got an extra proton there as well, okay? Because it's not silicon, it's phosphorus. So you've got a proton and an electron that's been introduced. Okay, so we call phosphorus an N-type dopant, and as I said before, the symbol for that is little n. Yeah, it's a little bit confusing because we've used N as electron density, but okay, N is still an electron dopant, so it's not too confusing maybe. Okay, so let's look at the other case here. We've done, okay, the phosphorus donor atom. This is called an acceptor atom. It's aluminium replacing a silicon atom. Now, aluminium has one less electron than the silicon, so the aluminium atom really wants another electron, but it doesn't have one, so it's got a hole on it. A hole meaning an empty electronic state. Okay, so it's indicated by plus here. And so you can imagine if you've got extra electrons somehow introduced into your system, those extra electrons will immediately occupy this empty hole state here. So we use P for hole density, and we call atoms that introduce holes, we call those acceptors. Why do we call them acceptors? Just like I said before, because they are accepting of an electron that may be in your sample. They like to accept an electron. So kind of to summarize, we have intrinsic system, for example, our silicon. We have on each atom 4 bonds with its neighbours. Each bond is occupied with 2 electrons, 1 electron from each atom. In an N-type doped silicon, we have an extra electron. It can be just drawn sitting there, somehow floating around. And we've also indicated here that there is an extra proton there in the phosphorus atom. The opposite here, we have P-type material. We introduced, for example, aluminium into the silicon lattice. It didn't have enough electrons, so there is a bond here that's only got 1 electron in and an empty state or a hole next to it. Another kind of electron dopant is antimony. Again, antimony, just like phosphorus, has an extra electron in its system, so it also is another example of an electron donor. Okay? The 5 electrons from the antimony will go into the bond with the other silicon atoms, and there'll be 1 left over. This again just illustrates aluminium as our acceptor dopant. Okay, so first of all, you could imagine that you might actually introduce a dopant atom that contributes not just 1 extra electron, but may introduce 2 extra electrons, or 3 or 4. Okay? Same with the acceptor, you may introduce a dopant that doesn't introduce just 1 hole, but it may be short of 2 electrons. It's still an acceptor, but it introduced... I just want to emphasize that these donors and acceptors don't always just have to contribute 1 electron or 1 hole. It can be more. Remember we had, for the case of 1 electron dopant, like the phosphor or the antimony, we had an extra electron and we had a positive proton left behind. The way the binding of that electron to that hole, because they're attractive, right? You've got a proton left behind and an electron wandering around. They still feel the presence of each other due to the Coulomb attraction there. So the way you normally describe that kind of binding of that electron is by saying it's very similar to a hydrogen atom. Okay, hydrogen atom, you just have one proton and one electron, and this is from your quantum mechanics. You will just have the description of that proton and electron through this kind of Rydberg energy. Okay? So similar to the hydrogen atom, we have for a hydrogenic impurity, which is one that just contributes one electron and has one proton behind. We can approximate its energy by being just that of the hydrogen atom, 13.6, and then it's just modulated by the effective mass that that electron has relative to the normal electron mass, and we have here the permittivity. And you can, there's an effective radius that impurity system had, that extra electron with the proton. And again, it's equal to the lattice A0 here. For example, for hydrogen atoms together, 0.51 angstrom. And so the effective radius, if you like, that electron and that hole sort of can interact with is given by the mass of the electron divided by the effective mass of the electron. So that's one way of describing the interaction of that extra electron with the positive proton that was left behind, just like a hydrogen atom modified by the effective mass. That's sort of mainly the same as what I have just said. So sometimes we haven't really looked at the energy levels that the donor atoms introduce into the semiconductor band structure. If we consider here, this is your field valence band, which is just drawn as a block, but often it's sort of, as a function of K, it's a parabola shape near the valence band maximum. When you introduce donor impurities, they will give rise to electronic states just below the conduction band minimum. And because you are doping lots of them, you'll get lots of different little, or very similar, if it's the same species, electron states here. Okay? So normally, to be a donor, you have to introduce an extra electron or more, and your energy is just below the conduction band, okay, to be a good donor. Because you want your electron, your extra electron, which is sitting here, with just a bit of temperature to be able to jump up into the conduction band. Okay, so this energy difference has to be small. If you introduce an impurity into your crystal that has a corresponding eigenvalue right in the middle of the band gap, it's not going to be any good to be a donor or acceptor, because the energy difference from this position up to there, it's too high. It will never be able to get excited into the conduction band. Good donor electron states of your donor close to the conduction band minimum. Conversely, to be a good acceptor, your introduced eigenstates need to be close to the valence band maximum. Okay? Why? Because then the electrons in the valence band can easily jump up into these states and leave behind a hole, which is what you want. This is the hole doping. So empty states here from your acceptor close to the valence band maximum, so that electrons in the valence band can jump up into these states and leave behind a hole. Okay, this just shows some actual values from some research that has been done. What have we got here? So here you can see this is silicon, has a band gap of 1.1. This is your valence band down here. This is your conduction band up here. Acceptors have been introduced into your system, for example, aluminium that we have talked about. And you can see that the aluminium has given rise to an eigenstate or an energy state 0.057 eV, just above the valence band maximum. And so that's really close. And again, here boron is also, these are very good values for acceptors, very small. This value represents the energy from here, valence band maximum, up to there. Okay? So 0.065 from here, energy 0, call that, up to there. So that electrons can easily be excited from here up into there, leaving behind a hole. Up here we have, remember our donors, antimony and phosphorus. You can see the 0.04 corresponds to the energy from the conduction band minimum just down to this eigenstate here. So this is very close to the conduction band minimum. So that's a very efficient kind of electron donor. So the electron will go from here. This is, will have an electron in, and it will be excited up into the conduction band where it can move around. This is also quite small and also quite small. So these are very good donors and acceptors. Okay. And yeah, this is a huge field of research that goes on. I just want to see whether I've got anything here that I haven't told you already. Maybe it illustrates a bit more clearly what I tried to say. Okay, so this is now for an N-type material. You've got extra electrons in your system. They have introduced defect level or eigenstate here just below the conduction band minimum. You can see it's occupied with some electrons in the band. What happens is that those electrons can go up into the conduction band at some elevated temperature. So I hope that's clear. Conversely, it's just more text. I want to go to the acceptor. So remember the acceptor here introduced an energy level that's empty, okay, empty, and with a bit of temperature, electrons from the valence band can jump up into those states and occupy that state, leaving behind these holes, which are then the mechanism for conduction in P-type material. Okay, I want to leave it there. Just leading up to tomorrow's lecture, we're just going to look a bit about how these concentrations can be calculated. Okay, so we're drawing on the Fermi function and so on. Okay, I think I'll leave it there for today. Yeah, I just want to say about the assignment. number 2, it's already up, and probably there's some stuff on it that, yeah, we haven't actually gone through yet, but don't worry, we'll get to that and by the end of the course. Okay.
J'ai pas dit que je venais pas, hein, déjà. Attends, tu me laisses genre 30 secondes pour t'expliquer ce que je veux faire ou pas? Oui, bien. Tu allais me balader quelque part? Quoi? Tu allais me balader quelque part? Attends, je pense que je vais les mettre. Je pense que, étant donné que j'ai pas petit déjeuner ce matin, je vais d'abord aller me prendre un truc à bouffer. Genre le manger tranquille chez moi. Et peut-être après, je peux